All right, hi everyone. Here is another practice problem regarding Bernoulli's. So here you have a small diameter, high pressure liquid jet that actually is used to cut materials. Okay, so there's some sort of liquid inside this jet. I believe we're going to use water. Okay, that shoots out and actually shoots out at 700 meters per second. And what we're going to do is trying to figure out what the pressure is needed inside this nozzle. Okay, it says if viscous effects are neglected, meaning the water touches the inside of these surfaces, all right, and it creates friction, but we're going to neglect that. There's also friction created with the water outside in the atmosphere, but we're going to neglect that too. All right, so we want to figure out what the pressure is if we know this jet diameter. So here, if you look, the red is like the top of the liquid layer, and above that, it's pressurized. And here you have this path that the water is going to travel, which is this purple path. Shoot, and then it goes right out. So along this one path, energy is conserved of the fluid. So if we pick our point 1 to be right here, which is like the water or the liquid air interface, and then point 2 being right outside the nozzle, okay, energy is conserved between those 2 points, okay, because it's kind of following one direct path, which is that purple path. Whoops, let me undo that. There we go. All right, so we can use Bernoulli's conservation of energy of a fluid as state 1 and set it equal to state 2, which I did down here. Okay, so P1 over rho plus V1 squared over 2 plus GZ1 equals P2 over rho plus V2 squared over 2 plus GZ2. Okay, now if you look over here, our assumptions, steady state, okay, that means the liquid layer is shooting out at a constant flow rate all the time. It's incompressible, the water, all right, there's no Q and no mechanical work. All right, so no Q means it's an adiabatic system, so there's no heat transfer between the surroundings to the water. And W is mechanical work. There's no like paddle wheel, there's no electric resistor, there's no mechanical object doing work. Okay. And here, what we did is we assumed that on the left-hand side, this point 1, that the velocity is relatively small compared to the velocity shooting out at 2. So we neglect that. It doesn't say anything with altitudes, and you could put the altitudes in if you knew the height differences, but they're going to be small, so you can neglect the altitude changes. Okay. and if you picked your datum at 2, there would be a small height difference, but it's so small we just neglect it. It shoots out to atmosphere, and that gauge pressure is 0, so that's why P2 is gone. And we end up with P1 equals rho V2 squared over 2. And I'm just doing gauge now because I did P2 as gauge. So I plug the numbers and I get 2.45 times 10 to the 5th kilonewtons per meter squared. That's a lot of pressure to shoot that out at 700 meters per second. All right. Now to find the flow rate, just use conservation of mass. V dot equals a 2V2, and we plug our values in and we get 5.5 times 10 to the minus 6 meters cubed per second. All right. So just to recap, Bernoulli's conservation of energy of a fluid, and that fluid should follow a path. Okay. This purple line actually is what they call a streamline. It's what the fluid from like a fluid particle at point 1 would do as it travels towards point 2. It would follow this purple path, and they call that a streamline. Okay, so along this path or streamline, that's what conservation of energy is conserved. Okay, thank you.